Welcome to the first video on exponential and logarithmic functions in Chapter 8. What you've just done, hopefully with your partner, is looked at completing the table for the first 6 weeks of pay for what my parents would have to pay me according to this plan. And hopefully what you filled out was the following. On week 5, you'd have 16, which is the same as 2 to the power 4, 2 to the 4th. And the 6th week, it'd be 32 pennies, which is the same as 2 to the 5th power. And on week X, depending on what week that is, we can't really calculate that, but in general, if you notice the pattern between the week number and the exponential form, you would notice that every single time, the exponent for 2 is 1 less than the week number. So on week X, I'd have 2 to the power X, take away 1 power. So using that exponential form for week X, we could have computed the amount that I'd receive after 31 weeks. It'd be 2 to the power 31 minus 1, or 2 to the 30th power, which is this amount. I have to write it down and get the commas correct before I even can say it right, because it's quite a large number. If you put that in your calculator, let's see, we're in the thousands, we're in the millions, we have cracked into the billions. So it looks like it's 1,073,741,824. That's how many pennies I'd get on the 31st week, and that doesn't include all the pennies that I received before. Now, how much is that in dollars? Well, if that's how many pennies, we'd have to divide by 100, right? And move the decimal place over twice. So really, it's not quite a million anymore, right? It'd be 107,374,118.24. So my parents would owe me a cool $10 million on that 31st week. So what apparently started off as a kind of a lousy deal, at least that's what it seems like, right? Getting only 1 penny and 2 pennies and 4 pennies and 8 pennies. I mean, geez, there's weeks I'm basically going without pay, but eventually that thing just takes off and skyrockets, and it gets huge in a hurry. So no, my parents were not able to pay up, and actually they figured out pretty quickly that the gig was up, and it wouldn't be a very good deal. And then I complained, and I got good stuff later for them giving up on their end of the deal. Anyway, what then you were supposed to do is, if you were to graph your function on the worksheet, you'll have your first exponential growth function. And at week 0, we had only 1 penny. Week 1, or excuse me, we didn't really plot that first 0 mark, did we? So at week 1, we had 1, and then week 2 was 2. Week 3, we had 4. Week 4, we had 8, in week 5 we had 16, and so on. So if you were to try to connect these points, these things, you can see they just skyrocket very, very quickly. So let's take a look now at what's really going on. Section 8.1 is on exponential growth, and the curve that we just drew is an exponential growth curve. We're soon to learn that the curve that best fits that data has the form y equals a times b to the x and is an exponential function. The reason why it's called an exponential function is because you'll notice the independent variable x is now as an exponent, and you've never worked with that before this chapter. So that's why they call it exponential functions. The variable x is now in the exponent. Before we get too involved, let's look at some basic exponential functions. Y equals b to the x, where b is called the base, and it's a positive number other than 1. So let's take a look at some graphs of those. The first example, we're going to graph 2 to the x, which is very similar to what we just looked at. And we're going to do it where we just plot a lot of values, so we really get a good idea of what's going on. So remember, f of x is really 2 to the power x. If we did 0, remember, 2 to the 0 power 2 to the 0 is really just 1. If we did 2 to the negative 1, that's not negative 2, guys. Remember, it's a negative exponent. That'd be really 1 over positive 2, a half. If we did 2 to the negative 2, that would be 1 over 2 squared, which is 1/4. If we did negative 3, that'd be 2 to the negative 3, which is the same as 1 over 2 to the positive 3, which is the same as 1 over 8. Let's do one more in the negative direction. 2 to the negative 4 is really 1 over 2 to the positive 4, or 1 over 16. Let's go to the positive direction. If we did 2 to the first, you know that's just 2. 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16. So you can see as we go to the right, the numbers double, and as we plug in the negative numbers, they get halved. We're multiplying really essentially by a half every time. If we plot these points, we'll get kind of an interesting looking graph here. So let's start at 0. When we plugged in 0, we got 2 to the 1. When we plugged in 1, we got 2 to the half. And when we plugged in negative 2, it was to the 1/4, and then to the 1/8. And these points that we plot going to the left get closer and closer to the x-axis. But think about it. If you did like 2 to the negative 10, are we going to get a negative number for y? Well, so if we were to plug in x is negative 10, we'd have to compute 2 to the negative 10. That'd be 1 over 2 to the positive 10, which is 1 over a really big number. But it's not negative. What that is super, super close to 0, but it doesn't quite get there. So what's going on with this graph is as we plug in negative x values, it gets closer and closer and closer to the x-axis, but it never quite touches it. It's impossible to touch the x-axis on this function. As we go to the right, what happens is this thing takes off. When we plugged in 1, we got 2, 2, we got 4, 3, we got 8, and then I can't even plot 4/16 because it's already off the chart, so this thing just takes up, off, and I'm going to put an arrow on it to indicate that it's just going to keep climbing and climbing. So here's the function y equals 2 to the x. Let's think about the end behavior for this graph. Now, I'm going to kind of use this notation as x goes to infinity. Guys, all I'm saying then is as x goes to infinity, I'm talking about what is going on to the graph as we go in this direction. Well, as we go in that direction, you can see the graph is taking off, going upwards to positive infinity. So what I would write here is the function f of x. Remember, these are like your y values. Those y values are increasing. They're going up, up, and away, and they're not going to turn around. They're going to go up as high as you can possibly go, depending on which x value you're plugging in. Now, as x goes to negative infinity, that just means what's going on with this graph as I'm going in this direction to the left. Well, here the graph doesn't go to negative infinity, does it? It kind of just flattens out, and it's skimming along the x-axis there. But remember, it never quite hits that. So if you think about it, these values, as you keep going further to the left, get closer and closer to 0. Remember when we plugged in negative 10, we really got an output that was super, super close to 0. So we'll say that here the y values get close to 0. So because that happens, because f of x goes to 0 as the graph moves further and further from the origin, at least going in that left direction, right? The graph has the line y equals 0. That's just the horizontal line. Really, guys, remember that's the x-axis. If we kind of review Algebra 1, Chapter 2, that's just a horizontal line that goes through the origin. It's got that line, y equals 0, as what's called as an asymptote. And that's kind of a cool word. It's spelled A-S-Y-M-P-T-O-T-E. And an asymptote is just a line that a graph approaches as you move away from the origin. And we're going to use that as a guide when we graph these things. Here in this box are some general guidelines for these exponential functions that are of the form a times b to the x. the graph will always pass through 0, and if you think about it, if you plugged in 0 into this general form, a times b to the 0, doesn't b to the 0 just become 1? So it's just a times 1. You just get the a value. So 0a, that is meaning that the y-intercept is always going to be the a value. That's like kind of the leading coefficient there, the coefficient of the exponential function. The x-axis is always going to be the asymptote for the graph. The domain is not restricted. It's all reals. You can plug in negatives, positives into these exponential functions, kind of like we did in this table, right? We could have plugged in any x value we wanted. However, the range, we didn't get all the possible y values out of this thing. The range is going to be all y values, let's say, that are greater than 0 only if a is positive, and it's going to be all y values less than 0 if the a value is negative. And what I mean by that is, if you take a look at our graph that we just had here, it's too bad I have all this extra stuff on it. Let me see if I can erase some of it. If you take a look at that graph, and let's only consider y coordinates on that graph, right? If we only look at the y coordinates that are on that graph, think about it, the lowest you can possibly get for y values are really, really close to 0 over here. And as you move to the right, all these y coordinates are going up, up, up to infinity. You don't have any graph that goes down here below the x-axis. So that's why our range is going to be y values strictly greater than 0 if we have that positive a value. Let's graph some. So in your homework, you're going to have some basic graphs that are like these. I'm going to ask that you plot 3 points, and then you just kind of use the fact that you have these asymptotes and know what these exponential functions look like to finish it off. Okay, so here we go. If we're going to graph y equals 1/2 times 3 to the power x, what I'm going to do is first let's plot a couple points. If we were to plug in 0, we can just calculate if we wanted, and I'll show you again what happens here. But if we plug in 0, we're going to get 1/2 times 3 to 0, which is just 1/2 times 1, or 1/2. And remember, anytime you plug in 0, you're really just going to get that a value anyway. So that would be the shortcut. If you plug in 1, it'd be 1/2 times 3 to the first, which is 3 over 2. That's the same as 1.5, right? That's 1.5. If we were to plug in 2, we'd get 1/2 times 3 squared, which is 1/2 times 9. And if you cut 9 in half, I think you get 4.5. So we'd have to plot 2, 4.5. If we plot these coordinates, 0, 1/2, and then when we plugged in 1, we got 1.5. When we plugged in 2, we got 4.5 right there. You can see this is kind of like that y equals 2 to the x graph. But now, remember, we have the line, or the x-axis is our asymptote. This is our asymptote, remember. So we do not want to cross over the x-axis at all as we go to the left. The line's going to just get closer and closer and closer to the x-axis without touching it, and as we move to the right, this thing grows exponentially, and it just takes off up and to the right. Okay, let's take a look at B. Now B, do we do domain and range? Let's talk about domain and range real quick. Domain would be all reals. You can plug in any x value you want. The range, however, is only y values that are strictly greater than 0. You can't get a y coordinate that's negative as an output for that graph. Let's do B. I have the opposite of 3/2 to the x. Now here, the a value, the coefficient, is really -1. So when I plug in 0, I would get out negative 1. If I plugged in 1, I'd get the opposite of 3/2 to the first, which is just -1.5, right? So I get -1.5, and if we plug in 2, it'd be the opposite of 3/2 squared, which is the same as the opposite of 9/4 if you square the 3 and the 2. That's what, -2.25, I believe. So -2.25 if we were to graph it. So 0, 1, or -1 rather, would be right here. Then we had 1, negative 1.5, and then 2, negative 2.25 is about right there. The x-axis is still the asymptote. So as we move to the left, this graph gets closer and closer to the x-axis, but never touches it. And as we go to the right, this thing drops down and down and away. Kind of like the exact reflection of the previous graph that goes up and away. And you might be guessing right now, what is making this one go down and have negative outputs is the fact that that a value is negative. So when we talk about domain and range, your domain here is still all reals, but your range is all y values now that are strictly less than 0. Okay, let's do a couple more that are what I call the Big Daddies, where you kind of put everything together. Now for the Big Daddies. Now, if you take a look at these, the hardest ones that I can possibly give you are of this form. And if you notice, it's just got an H guy and a K guy. And if remember from the last chapter, H was simply a horizontal shift. K is a vertical shift. So we're going to do the same thing we did before. First step is to graph the parent function. This is your parent. Oops, I don't want to write rarent. Parent function. And we do that by ignoring the H and K value altogether. Okay? Then we'll take a look at what H and K is and shift accordingly. Let's do a couple together and then I'll stop this video. So first one, we have y equals 3 times 2 to the x minus 1 minus 4, and then we're going to do the domain and range. The first thing that I'm going to do is absolutely ignore the H and K. My parent function then is y equals 3 times 2 to the power x, which passes through 0, 3. If we plugged in 1, we'd get 3 times 2, which is 6. If we plugged in 2, it would be 3 times 4, which would be 12. So let's graph that. 0, 3. We got to do 1, 6. And then 2, 12, which is a little bit off the chart. Let's just say it's about there, right? And now let's worry about shifting, kind of like what we did in the last chapter. Oops, I didn't want to do that. I wanted to erase and uncover my shifting. Now, the K value is just like it was before. When you see an x minus 1 in the exponent, it really means my K value, or excuse me, not my K value, what am I talking about? It's the H value, right? That's my H value is really positive 1. So we're going to go 1 to the right horizontally, and my K value is negative 4, which means 4 down vertically. So I'm going to move each of those 1 to the right and 4 down. So this guy, 1 to the right and 1, 2, 3, 4 down. Now it's here. This guy goes 1 to the right and 1, 2, 3, 4 down. So 4 down, 1 to the right, 4 down. And this guy is going to go 1 to the right and 1, 2, 3, 4 down right there. So really my final graph goes through these points. Now the other thing that got shifted to the 1 to the right and 4 down, actually, remember there's an asymptote that's on the x-axis normally. That thing also got shifted 4 down to its new home down here. My asymptote now is not the x-axis. It's y equals negative 4 because everything got shifted 4 down. So what that means is I don't need the x-axis as my asymptote. Really, I start close to this new asymptote and I move up and to the right through these coordinates. And my domain is still unaffected. It's all reals. My range is just y values that are strictly greater than negative 4, the new asymptote value. Let's do one last quick example before I let you guys loose to try some on your own. First, graph the parent function y equals 2 times 3 to the x power. You're ignoring the shifting. That's going to go through 0, 2, 1, 6. And if you were to plug in 2, you'd have 2 times 3 to the second, which is 2 times 9. That's too tall to plot. So sometimes, instead of plugging in 2, guys, what I like to do is plug in negative 1. And that might give you a nicer point to plot. So that'd be 2 times 3 to the negative 1. That's the same as 2 times 1/3, right? You move the 3 downstairs. That's 2/3. So let's plot those points. We're going to have 0, 2. We have 1, 6. And when I plugged in negative 1, I got 2/3, which is about there. Now we have to worry about shifting. Here, h value is positive 2. That means 2 to the right. Right, that's our k value, or excuse me, I keep mixing those up, sorry. H value is really positive 2. The k value is 1, which is 1 up. So I'm going to take each of those and go 2 to the right and 1 up. So I'm going to start with this guy. 2 to the right, 1 up, right there. This guy, 2 to the right, 1 up, right there. This guy, 2 to the right, 1 up, is right about there. So let me erase the nonsense I don't need. And this guy was 2 to the right and 1 up. That was about right there. Now remember, the asymptote is no longer the x-axis. That got shifted 1 up. Now it's the line y equals 1. It used to be the x-axis, but it got shifted up 1. By the way, notice how I'm dashing my asymptote when it's not on the x-axis? I need you guys to do that. Do this on your homework. I should see this. When your asymptote is not on the x-axis because it's got shifted, you should be dashing that. So I'm going to start close to the asymptote, and as I move to the right, it's going to go up, up, and away. And so our domain is all real, and the range is all y values that are strictly greater than 1 now since our asymptote got shifted up. Thanks for watching, guys.